Okay, so in this video, we're going to take a look at vector valued functions, beginning with space curves and vector valued functions. And we can start by kind of thinking about plane curves, which we defined as x equals f of t, y equals g of t. So this is basically just parameterization. And when you're dealing with space curves, you might be able to predict that all you want to do is extend this into the third dimension. And you can probably also go ahead and predict that if you run x and y, you're going to move on to z next. If you run f and g, you're going to move on to h. And that's precisely how we do it. Right, so you're just adding another parameter now, z equals h of t. And so in a plane, you'd have a function like r of t is f of t in times I, which is a unit vector in the x direction, plus g of t j, which is a unit vector in the y direction. And when you're dealing with space, you just add the z dimension now, right? You're adding this one over here. And this is just a vector valued function. So instead of writing it like this, you can also write it in this form. So you're just writing it with the different components within the angle bracket. So right there. That's another way of writing it. Exact same thing. They're completely interchangeable. Two graphs. So you can have the same graph, the same shape, even if you've got different curves. And you can look at that here. What's going to change is how you trace that graph, right? Like sine of t, cosine of t. Here you've got sine of t squared and cosine of t squared. So you can imagine that for the same values of t, the values of um, r might be different for each of the curves, right? And that makes sense because t squared is going to change. And so even though you might get back to the same graph, which is tracing out a circle, you might trace it out more than once in this case, for example, right? Actually, you will end up tracing it out considerably more than one time. I think you'll trace it out 2 pi times, but don't quote me on that. Okay, and there's really not much else over there. We can talk about the domain. And the domain, if you go back to this definition over here, and hopefully this is intuitive for you, if you're defining a function that depends upon f of t, g of t, and h of t, it can only exist at points where f of t, g of t, and h of t all do exist, right? In other words, the domain of r of t can only consist of the intersection meaning f of t has to be satisfied, it has to be within f of t's domain, g of t's domain, and h of t's domain. No, you can't have a case where g of t is not defined, like maybe it's 1 over 1 over t minus 2. That's not defined at t equals 2. Even if f of t is defined, even if h of t is defined, r of t cannot be defined because this component of it will not be defined at t equals 2. So that's why it's an intersection. Hopefully that makes intuitive sense. If you want to see an example, just take a look right here. There are no restrictions on t over here. Over here, t has to be, what is it, less than or equal to -1. Over here, t has to be greater than 0. So you can't, so you have to find something that satisfies all of those. So it has to be greater than 0, it has to be less than or equal to -1. This doesn't add any further restrictions. And so our final interval is going to be this, right? So it's a pretty small interval, even though t is defined everywhere in the z direction, that component is defined everywhere. You still have to be cognizant of the fact that that it's an intersection, right? However inconvenient that is the case. Okay, how about sketching a plane curve? How can you do that? Well, oftentimes you can convert it into rectangular coordinates. You'll probably be more familiar with those shapes and what they look like. And when you actually go about doing that, you're going to get this, which is an ellipse, right? It's a vertical ellipse actually. If you want to find the orientation and see which direction you're going to be tracing it out in, for that you can just plug in values. And I think that's the most convenient way to do it. Plug in like t equals 0, figure out where you are. And of course, it's also a good way to check your work that you did draw it correctly, because when t equals 0, you're going to get 2 times 1i, so that's right here, minus 3 times 0j, so that's still right here. And you can do a sanity check and make sure that you've drawn it out correctly. What about if you're sketching something that isn't quite so simple? This is in 2 dimensions. What if you're doing a space curve, which is in 3 dimensions? Same process, right? Over here we can look at the first two, and you can notice that would trace out a circle of radius 4. If you don't notice that right off the bat, don't worry, same procedure. You can just put x equals 4 cosine t, y equals 4 sine t, right? Because this is the x component, this is the y component. So that's all you have to do. You find the rectangular equation, and now instead of just tracing it out, you have to also think about t times k, right? As t increases, as you're starting to trace it out, you're also going to be moving up. So as you're tracing out the circle, instead of going around like this at the bottom and staying there, you're also going to be increasing your height, right? And when t equals 2 pi, you'll have traced out a full circle, but not on the xy plane. You will have been shifting your z value. You would have been increasing it, and now that value will have reached 2 pi, right? So you've traced it. If you look at it from like above the graph, like above the xy plane, on the z axis, it will look like a circle to you because of that angle. But from this angle, you're increasing the z values as well. So you need to keep that in mind. This shape is known as a helix. If you've seen a DNA helix like this over here, that's basically where it gets its name, or like vice versa. I don't know, but that's kind of like a little way that might be helpful to remember that. I don't know. What about representing a graph by a vector valued function? Well, you can let x equal t, then y is going to equal t squared plus 1. It's as simple as that, and then you just plug it into this, you're done. What if you're doing something a little bit more complex, like this over here? You're trying to find the intersection of y equals x squared with this semi-ellipsoid. The reason it's a semi-ellipsoid is because you've got z is greater than or equal to 0. So if you were to graph it out, it would give you a full ellipsoid, and then with this condition, you'd basically slice off the bottom half for all z values below the xy plane, meaning z is less than 0. You'd slice that off and you'd be left with half an ellipsoid, semi-ellipsoid. To actually go and do this, well, we can let x equal t. Then we know from this that y equals t squared. You can plug in t squared, squared, which is t to the fourth, plus z squared over 4 equals 1. Of course, keep these denominators in mind as well. Solve for z in terms of t. And they did that over here. And because we're given that z is greater than 0, where was that? That was here, right? Z is greater than or equal to 0. You will take the positive root, not the negative root, not plus minus, just the positive root. And then you plug that in, and this is what you get. Now, if you graph it, you can see it's not the prettiest graph, but at least it makes sense, right? And you can see the orientation as well. It's going this way. Okay, let's talk about limits and continuity. Limits here, I think, are very, very straightforward. They're very intuitive, at least to me. It's basically the same process as you'd have for other functions. If you add them up, you just add up the, okay, sorry, no, this is just with functions. This isn't even with limits, right? Over here, r1 of t plus r2 of t, you can break it up by components, add the components of each of them, just like you'd add vectors, really, right? Instead of adding vectors, you're adding vector valued functions, but it's the same thing. You just do it component wise. Same thing with subtraction. Multiplication, you're multiplying it by a scalar, so you just do cf of 1, cg of 1. Dividing, same thing, same constraint, c cannot equal 0, right? Nothing has changed over there fundamentally. What about with limits? Well, the way it's defined, this is also very convenient for us. You just do it by components. So if you want a limit of a very complex function, just look at the less complex components of the function. Hopefully they're less complex. And then if that limit exists, then the limit of your vector valued function exists, right? That's really all it is. Continuity occurs when you've got t equals a, and the limit as t approaches a of r of t is equal to r of a. So when you're going to a point and then and when you reach that point, realize that, hey, the point that I'm going to is the actual point on the curve, right? That's continuity. And it's implied over here because there's no plus or minus, that it should be from both directions, right? And so in some trickier cases, you might have to prove it separately from both directions, but generally just proving this is fine, right? If this limit exists, then you know that the limit from the negative and positive directions are the same and they're equal to that. Let's take a look at an example over here. So take the limit as t approaches 0 for all of these. What are you going to get? You're going to get aj and then a squared k. And when you actually, right, that's a limit. When you actually plug in 0, you also get aj and a squared k. So you know that these are the same. Thus, it's continuous, not throughout. All you know from this information, where you've done t equals limit as t approaches 0 and r of 0, is that it's continuous at t equals 0. But you can extend that to other points and to like in general as well. That's really all there is in this section. The next section will kind of go into, let's take a look actually. Then the next section goes into differentiation and integration. So let me know if you want to see a second video in this series, and I'll be sure to make that. Thanks so much for watching.